Chapter 16, we're looking at spontaneous reactions and free energy. We need to do a couple of definitions, so we'll start out by defining spontaneous reaction. Spontaneous reaction, as you might expect, is a reaction that occurs without any outside intervention. It happens all by itself. Spontaneous reactions can be determined if we look at the delta H sign. If we remember back from chapter 6, we remember that when delta H is positive, we have an endothermic reaction. When delta H is negative, we have an exothermic reaction. Endothermic reactions usually need help, usually need to have heat added, and so they tend not to happen by themselves. Exothermic reactions giving off energy are more likely to be spontaneous. Remember that delta H is a measure of heat flow. It tells you whether heat is flowing into the system or out of the system, and heat always flows from an area where it's warmer to an area where it's cooler. Thermodynamics tells us if a reaction is going to occur, but it doesn't tell us how long it will take. So it gives us the if, but not the how long. Kinetics, remember, is what tells us how long something will take to react. We saw a little bit earlier that when delta H is positive, it's an endothermic reaction. When delta H is negative, it's an exothermic reaction. Heat of formation, standard heats of formation for elements. Remember, for elements, heat of formation is 0. Some reactions are spontaneous at a high temperature, but aren't spontaneous at room temperature. We take calcium carbonate. Calcium carbonate decomposes to calcium oxide and carbon dioxide. We have a delta H of positive 178 kilojoules. So it's an endothermic reaction. The reaction requires energy, as delta H tells us. But if we have this reaction running at a high enough temperature, if we supply enough energy, it will go by itself. So delta H doesn't depend on temperature, but temperature is involved in determining the spontaneity of the reaction. So if we look at this chart that we have here, this graph, where we have energy on the vertical axis and the reaction coordinate on the horizontal axis, essentially we can break this down into two pieces, a thermodynamics portion and a kinetics portion. So initially we're looking at the reactants and products. So the reactants start out with a particular amount of energy. We've seen this particular graph before. So this is the thermodynamics portion of the graph. This middle portion here we have our activation energy. So this is kinetics. So the middle portion of this graph is the kinetics portion of the graph. Then we end up with energy down here, so we're back now to thermodynamics. So all reactions involve both the thermodynamics portion and a kinetics portion that tells us, first of all, if it will occur, and second of all, how long it will take to run as a reaction. We already saw it happen with calcium carbonate. Water is another example. If we go from solid water to liquid water, so we're melting, we have a delta H of positive 6 kilojoules. So it's endothermic. We said earlier that endothermic reactions tend not to be spontaneous, but at room temperature will ice melt? Yes, we see ice will melt very easily at room temperature. So even though this is an endothermic reaction, it's spontaneous at room temperature. So something else is going on here. And the other thing that's going on is entropy. Entropy is crucial to figuring out if something is going to be spontaneous or not. Entropy is the driving force for any reaction, and to increase the entropy is essentially the goal of the universe. There are two driving goals of the universe, and we'll take a look at them when we look at the laws of thermodynamics. Definition for entropy is it's the measure of disorder or randomness present in a system. So if we take a look at a particular system where we have 4 particles, in arrangement 1, we have all 4 particles on one side. So we essentially have 1 degree of freedom in terms of their position relative to each other. We now move 1 particle to the right and 3 particles to the left. So we have a couple of ways that those could be arranged. If we number our particles 1, 2, 3, 4, because over here we could have particle 1, we could have particle 2, we could have particle 3, or we could have particle 4 be the singleton. So now we have 4 degrees of freedom as opposed to just 1 degree of freedom. The next option is we have 2 and 2. So it turns out there are 6 different ways, 6 degrees of freedom now in terms of what particles are where, whether we have 1 and 2, 3 and 4, or whether we have 1 and 3, 2 and 4, etc. You get the idea. Another way is we have 1 particle on the left, 3 particles on the right. It's essentially the reverse of arrangement 2, so it would make sense that we have the same number of degrees of freedom here. And arrangement 5 is exactly the reverse of arrangement 1, so again, 1 degree of freedom. So what we're looking at is how many particles do we have and how many different ways can we arrange those particles. The more ways we can arrange the particles, the more random or disordered the system will be. All right, if we take a look at this diagram, we have two sets of elements on the right. We have hydrogen and we have nitrogen. They're both diatomic. And since we have two different things, they can be in a variety of different places relative to each other. Here we have a compound of ammonia, and since it's all the same, there's really only one way that they can be organized relative to each other, and that is next to other ammonias. So when I put the elements together in a compound, I diminish the number of ways I can place them relative to each other. If I look at a single molecule, when I have multiple atoms in a molecule, I can have those atoms sometimes in different positions relative to each other. An example is a water molecule. Now the only way I can organize it is to have one hydrogen attached to the oxygen and the other hydrogen also attached to the oxygen. So they're fixed in their position relative to each other in a rigid structure, but water molecules are flexible. They can have vibrational rotations where the hydrogens move closer to and farther away from the oxygen molecule. They can have vibrational rotations where the two hydrogens are moving closer to each other and then further away. So in this first case of vibrations, they're moving simultaneously. In this case of vibrations, one hydrogen's moving away from the oxygen, the other hydrogen's moving closer to the oxygen. So in all three cases, the hydrogen's positions relative to each other changes. And because it keeps changing and it may be different in molecule A compared to molecule B, we have some randomness going on. In addition to these vibrations, we have the whole molecule spinning. So if you remember the three-dimensional structure of water, the two hydrogens can be in line parallel to the next molecule, or they could be rotated so they're 90 degrees in orientation relative to the next molecule. So again, that increases their ability to be random compared to other molecules.